Hey folks, so this is the first lesson for Unit 2. You'll notice it's basically all up. Again, the mark sheet is up, all the information is up. I've reworked it so that everything can be done from home. So the first lesson in the first unit is exploring space. By the way, when you're done, the worksheet, either take a picture of it, and if you did it by hand, and then just email it to me, or if you did it as a Google Doc, just share it with me and I'll give you a question for your points. So, exploring space. So the idea of Unit 2 is our ship is basically taken off, and what we're now doing is we're leaving the solar system. So we're going to look at the basics of space travel. How do we know what is in our immediate vicinity? And how might we know what's farther away? So, exploring space is something humans have actually done as long as there have been humans. We started off basically with the human eye, looking up at the night sky and looking at the points of light, which are the stars, and a few planets. So ancient astronomers charted the position of stars over time using nothing but observation, and there are some beautifully detailed results of the motion of all the stars and comets and supernova and all sorts of weird things, even dating back to ancient times from their observations. In fact, the Romans used to use the stars you see here, the Pleiades, to determine who were going to be archers, because most people can see about 4 or 5 stars in that cluster, but people with really good eyesight can see 7 or 8. So, telescopes are a little bit better than the eye. Okay, big misconception with telescopes. They are not designed to magnify. They are actually designed to collect more light and bring more light to your eye. So if they do magnify the image, you get more resolution. So, I mean, you could stick any magnification eyepiece you want on a telescope, except the image would be incredibly blurry. It'd basically be like this, what happens when you take a computer image and you really pull it, and zoom in, it loses a lot. Unless it's an HD image, it loses a lot of its definition. Telescopes are kind of the same way. So you need a big objective lens to get as much light so you get as much resolution as possible. So the first person to use a telescope for science was Galileo. By the way, Galileo did not invent the telescope. He also never bothered to tell anyone he hadn't, and it was actually a toy he saw at a carnival made by a Danish lens maker. And in fact, Galileo made his fortune selling this children's toy to the Spanish Navy, because for a naval power, being able to see ships coming 2 hours away was a huge, huge advantage. That's actually where he got all his money from. So the telescope he used was called a refracting telescope. So it has 2 lenses, an objective, a big one, and then an eyepiece. So the objective lens basically focuses the light into your eye so you get as much resolution as possible. Most telescopes are now based on something Newton developed called the refracting telescope, which uses a mirror instead of a lens. The reason for this is making lenses is extremely expensive. The biggest refracting telescope in the world is in Hawaii, and it only has a 1-meter lens, and that cost over $15 million just to make that lens. So if we want telescopes to be really, really huge, it's a lot cheaper to make a mirror than to make a really big lens. In fact, you can get a kit to make, a telescope that's, 10 to 20 inches for a couple of $100 as opposed to, 15 million. However, the problem with telescopes on Earth is they have to deal with clouds, and, well, there's a reason there's no telescopes, observatories in our empire. There are clouds for half the year. That's why most of the telescopes are actually in deserts, so that you get away from the moisture and the clouds. But if we put a telescope in space, like the Hubble Space Telescope, even though it's about 20 years old and only has a 2-meter diameter lens, it can still get a much clearer picture than anything else and can see much farther away because it's not getting the fuzziness due to the distortion. One up from those are what we call radio telescopes. Now, what you're going to learn in grade 10 is light is just one part of a huge spectrum. So light waves, radio waves, infrared, X-rays, they're actually all exactly the same thing. And they all can be, we can get an image using radio waves just as easily as we can get an image using light waves. Radio telescopes are really good for looking at distant objects because the coolest thing is that you can make them really big, and if you can combine them to create what we call an interferometer. So you can take two telescopes, radio telescopes, and if you connect them together using a computer, it's like having one telescope that's the width of the two telescopes apart. In fact, this is how we got the picture of the black hole you've seen. We used 26 telescopes all over the Earth to basically create the effect of a telescope the size of the entire planet. Okay, what if we want to go there ourselves? Well, the big problem in space is not going up, but speeding up. And you've got to speed your ship up to a point that it either won't fall back down, so basically it'll be in orbit, so as it falls it'll be past the Earth and will keep basically falling forever, or actually escape the gravity of Earth and go somewhere else. So how does he do it? Well, Newton's third law. If you push on something, it pushes back on you with exactly the same force, even if it's moving. So it exerts a force backwards on the fuel. It shoots fuel out at very high speeds. That pushes the engine forward. It's the same reason when you let go of a balloon, it flies around the room, is that you let go and the air gets pushed out the back. That pushes the balloon forward. So the big problem is this. You need something to push out the back. And based on chemical reactions, there's something called the rocket equation. There's a beautiful video on it called The Tyranny of the Rocket Equation. It's a TED Talk. I'm going to put it up in the grade 9 folder on YouTube, and it's a really neat one to take a look at. But the biggest problem is that fuel's got its own weight. So for an engine to work, you need to provide more force than the weight of the rocket. And unfortunately, using chemical reactions, we're limited in that about 90% of the rocket's weight actually has to be fuel just to get it into orbit. That means you've got 10% for everything else, including the rocket. So it's really, really hard to get things into orbit because you need so much fuel. And that's one of the reasons why when we look at, in the next unit, getting interstellar, conventional fuel won't work because you just literally cannot get enough thrust for the weight of the fuel. All right, manned rockets. The first manned rocket was called Vostok 1. That's the one in the top corner here. That carried the Soviet astronaut Yuri Gagarin into space. Other famous ones are the Apollo capsules, which could hold 3 astronauts. They're the ones that went to the moon. The space shuttle could hold 7, and that's the biggest rocket we've ever made. So we've never made a rocket that can hold more than 7 people. So that's going to be the trick to, getting people interstellar, is that we're going to need way more than 7 people. You're going to need at least, biologists tend to say you need at least 1,000 people to make a viable colony. The space shuttle could also return to Earth. Unfortunately, again, because it was so big, so heavy, it required immense amounts of fuel. It was incredibly expensive to launch. That's why we don't use it anymore. There is another solution, and that's to launch a probe. So a probe is an unmanned vehicle that can take closer looks at things in the solar system. And they can be either satellite probes like Voyager or rover probes like Spirit, Opportunity, or Curiosity. Now, the advantage to a probe is, well, simple. It doesn't care if it doesn't come back. You don't need weight for food, oxygen, people, anything else like that. You don't have to worry about safety because if you lose the probe, well, we've just lost money. You haven't actually killed anyone. So probes are really useful for going out and getting information. Even on a manned mission, we'll probably want probes on our ship to basically go to the different planets and find one that's habitable before we get there. So probes are really, really quite useful. So that's the advantage of a probe, is that you don't have a human pilot. The downside is probes can only do what they're programmed for, and if you want them to look at something and if you launch your probe and there's something really cool, but you haven't put the piece of equipment on to look at it properly or analyze it, well, you're out of luck, whereas a human can sort of figure things out on their own. Probes also, if they break, they're broken because there's no one there to replace them. All right, so that's the basics of exploration. So, and that is Unit 1. Well, the first lesson for Unit 1. All right, bye all. Oh, sorry. I am not getting rid of you yet. I forgot there was an extra slide. Um, Humans also don't do well in space. Famous quote by Dr. McCoy from Star Trek that space is disease and danger wrapped in darkness and silence. And he's not wrong. Space travel leaves you weak, tired, sick, and possibly even depressed. A lot of us are noticing the isolation right now, how it's getting to us. You know, we're forgetting that there was another half of our slideshow. We're not functioning at our best. It's a big problem for astronauts too, if because they're basically quarantined in one little ship for months and months on end. So at launch, getting you into space, you're clearing the tower and the acceleration is building to 4Gs. That means your body feels 4 times its normal weight. So if you feel how much you're being pressed down in the chair right now, multiply that. Imagine you're being pushed down 4 times as much. It also pushes the blood into your feet and out of your brain if you're sitting like I am right now. That's why pilots are always laid back when they launch, so that they literally don't gray out, they don't black out, because the blood rushes away from your brain like it does when you stand up too quickly after teaching a lesson. So astronauts are oriented basically so that forces through the chest and it keeps the blood stable. Once you're in space, you have the opposite problem. You have weightlessness. And most astronauts immediately complain about nausea or vomiting because your brain really needs it down. You use your eyes to figure out what's down, and you use your inner ear for your balance. And in weightlessness, there's no gravity pulling down the inner ear, and your brain doesn't know which way is up. So astronauts actually practice on something lovingly referred to as the vomit comet. Microgravity flights that basically parabolic, they go up and down, giving you about 45 seconds of weightlessness as it does its arc over the top. And you can actually do this yourself. It's a couple of $1,000, but definitely worth doing in my opinion. All right, physiological effects. You get something called fat face. So being in space is like standing on your head. Your body is designed to push blood against gravity up to your head and push it easy and let gravity help get down to your feet. Because of that, your heart pushes blood up much more than it pushes it down. So you end up with a swollen face. So for example, if you actually look at Chris Hadfield, here he is on Earth, here he is in space, you can actually see there's a difference in their faces because of that extra blood flow. There's also some evidence that that might affect eyesight. It might actually have too much pressure on your eyes and cause eye damage. And with muscles, it's use it or lose it, right? So a lot of the body's systems depend on gravity to keep them conditioned. So each ISS member has to do an hour of cardio and an hour of weightlifting every day to make sure they don't lose the bone and muscle. Even then, when they get back to Earth, they are struggling to walk. They actually need a couple of days to get their muscles used to walking again. It also seems like it has an effect of causing the bone to almost dissolve away because it's not being used. There's no force on it. Sleeping in space is tricky because you don't have your normal circadian rhythm, especially if you're in orbit where you're getting a new day every 90 minutes. So the light-dark cycle doesn't work for you. And you have to get used to sleeping without lying down. We're used to lying down and relaxing. You basically have to strap yourself in so you don't float about the cabin when you're asleep. So what we've discovered on the ISS, you actually have these little sleep ports, these little sleep compartments where you can, it will automatically lower and raise the light so that you can simulate night effect. And people can actually, even then it's kind of hard to get used to sleeping on the ISS. Disease? It seems like there's a detrimental effect on the immune system of being in space. We're not sure if that's due to microgravity, radiation, whatnot. More concerning is cosmic rays. So on Earth, we're protected from the sun's cosmic rays by our Earth's magnetic field. Once you're away from Earth, you don't have that. So in fact, astronauts often see bright flashes of light, which are literally cosmic rays passing through their brains. The good news of that is NASA studies the Apollo astronauts who spent several days in deep space inside a really poorly shielded capsule, showed no incidence of increased incidence of cancer over their lives, and most of them have lived full lives and didn't see, any sort of negative effect. So that is the end of the lesson. So this is how we explore space. I'm going to put a few other videos up for you to look at. So the TED Talk is really, really good. I'm also going to put a few microgravity videos up. They're kind of fun. Um, and honestly, I encourage you to look through some of the videos and just sort of keep flipping around because they're actually a lot of fun. All right. See you for the next lesson, folks.